All right, so greetings, scholars. Let's see. So we're continuing our exploration on chapter 3, functions, and here we're going to be looking at section 3.4, composition of functions. A few learning objectives. In this section, you will combine functions using algebraic operations, create a new function by composition of functions, evaluate composite functions, find the domain of a composite function, and decompose a composite function into its component functions. So here we're asked to find and simplify the function g minus f of x, g divided by f of x, given this f and this g, and then are they the same function? Okay. So what we're doing with this section, you know how it's basically the algebra of functions, or arithmetic of functions. The same way we can add, subtract, multiply, and divide like numbers, we can add, subtract, multiply, and divide functions. You know, we're going to explore some of those concepts here. Then there's an additional concept aside from that arithmetic called composition of functions. So in this example, the first part we're subtracting two functions, and the second part we're dividing two functions. I want to warn you, a lot of times when students see this guy here, they think that we're multiplying by x, and that's not what we're doing, right? That's not what's going on. So don't distribute an extra x there. So here, let me get a copy of this. So it says find and simplify the first part. We have g minus f of x, right? And what that means g of x minus f of x. Again, we're not distributing. I know it looks like it, but that's not what's going on. The left hand part just means the function g minus the function f. Okay. So then g, now let's see if we're going to say the function g minus the function f. G is what? X squared minus 1. F is the function x minus 1. Notice how I plug the functions into a blank set of parentheses. So I do that because that helps us to keep track. Now we do need to distribute that negative. All right. Okay. So once we distribute the negative, we can lose our parentheses here because there's not going to be any more distributing or anything like that. So we have x squared minus 1 minus x, double negative becomes plus 1. Okay. Yeah, we can keep going. So then this is ultimately x squared minus x. Looks like they cancel each other out, right? A number plus its opposite. Okay. So for g minus f of x, we end up here. Now let's take a look at g divided by f of x. Sorry. Okay. So again, what this means the function g of x divided by the function f of x. We're not distributing. Okay. All right. Because if you start trying to distribute an x, you're going to get thrown off, and your chances of getting that question wrong are going to be drastically increased. Okay. So then g of x is what? X squared minus 1 over f of x, which is x minus 1. Okay. Now it looks like that numerator we can factor. Okay. Like this. Difference of squares, so it factors into x minus 1 times x plus 1. And the bottom stays as is. A number divided by itself cancels. And that one looks like it simplifies down to just x plus 1. Okay. Are they the same function? We would say not the same function, or no. Okay, so let's look at our prepared notes. So it looks like they got the x times, or the x squared minus x and x plus 1. So no, the functions are not the same. Okay. So note that for g divided by f of x, the condition x not equal to 1 is necessary because when x equals to 1, it makes the denominator 0, right? So we do need to, whenever we have we're dividing by a variable, we need to make sure that we're not dividing by 0. So we have to throw out x equal to 1 because it makes a 0 in the denominator for the second part. So when the output of one function is used as the input of another function, we call the entire operation a composition of functions. For any input x and function f and g, this action defines a composition function, which we write as f composed g, such that, right here. So f composed g of x is f of g of x, right? So what this symbol means is basically the second function. It means the second function inside the first function, right? So when we go to work these, one way you can do it is write, like for instance, write f like normal, whatever f is, and then we replace each x with the function g, right? So that's essentially what we're doing. The second function inside the first function. The domain of the compositional function of f composed g is all x such that x is in the domain of g and g of x is in the domain of f. It is important to realize that the product of functions f times g is not the same as the composition of functions f of g of x, because in general, f times g of x is not necessarily equal to f composed g of x, right? So just like in the previous example where we're trying to make it clear that, we're not distributing an x, another common mistake that students make is when they see this symbol, they think it's multiplication, or when they see it like this and they think it's multiplying. We're not multiplying here. This means the second function inside the first function. Okay. All right. So using the functions provided, find f of g of x and g of f of x, and then determine whether the composition of the function is commutative, right? So now we're trying to establish, is the order important when we take composition of functions, right? So the first one, we have f of g of x. So let me see. Okay, f of g of x, right? So we're going to do f of, what's my dark color? G of x, okay? So then this is going to be f of, now g of x is what, 3 minus x? Okay. All right, so what this means is that we're going to write f of x like normal, but we're going to replace each x with the green thing. So first we replace the x with a blank set of parentheses, and then what goes into the blank parentheses? The green thing. Right? So now we can just treat it like we just want to simplify it, right? So first we can like distribute the 2. Okay. So that's 6 minus 2x plus 1. What is that? 7 minus 2x. Okay. All right, so that's when we did f of g of x. We got 7 minus 2x. So now let's reverse the order and see what happens and see if the order is important. Now we want to do g of f of x. So then g of f of x. Okay. So our f of x is 2x plus 1. Okay. So what this means is we're going to write g like normal, but we're going to replace each x with the fuchsia color. All right, I think that's fuchsia. So when I looked it up, it's as close as it got. So anyway, 3 minus x, but again, we're replacing x with the fuchsia thing. So x now becomes this guy. Now we simplify. Looks like we distribute this negative here. So then it's 3 minus 2x minus 1. So 2 minus 2x. Okay. So notice that f of g of x is not equal to g of f of x. So it's not commutative. Right? We can say, I'm just going to copy and paste. Copy, paste. So f of g of x is not equal to, and in general, is not equal to, right? So f of g of x is not equal to g of f of x, so therefore this is not commutative. Okay. So in general, composition of functions. Sometimes when you commute it, they'll match, but in general, they're not commutative. Right? They don't necessarily always equal each other. As case in point. Okay. So we see that g of f of x is not equal to f of g of x. So the operation of function composition is not commutative. Okay. So the function c of s gives the number of calories burned completing s sit-ups, and s of t gives the number of sit-ups a person can complete in t minutes. So they ask us to interpret c of s of 3, right? C gives the calories burned on sit-ups, and S of t gives the number of sit-ups a person can complete in t minutes. So then if we say C of S of t, that's going to give us the calories a person can burn in 3 minutes while doing sit-ups. All right, it should give us the calories burned while doing sit-ups in 3 minutes. Okay, let's see what the thing says. So the inside expression of the composition is S of 3. Because the input of S is time, where t equals 3 represents 3 minutes, S of 3 is the number of sit-ups completed in 3 minutes. So using S of 3 as the input of the function of C of S gives the number of calories burned during the number of sit-ups to be completed in 3 minutes, or simply the number of calories burned in 3 minutes by doing sit-ups, right? That's exactly what we said. Man, why does this always happen to me? I'm sleepy again. I didn't take a nap between my other one, but I definitely went and ran some errands and came back, and I felt good. I was like, okay, I feel good. Let me go ahead and do this next video. 10 slides in, just I got a good amount to go. I'm ready to, hang out with Pastor Pillow or something, go to sleep. Anyway, let me see. Suppose f of x gives miles that can be driven in x hours, and g of y gives the gallons of gas used in driving y miles. Which of these expressions is meaningful? Let me see. Let me read that again. Ow. Suppose f of x gives the miles that can be driven in x hours, and g of y gives the gallons of gas used in driving y miles. Let me see. Okay. Which of these expressions is meaningful? I feel like I should relabel these. Let me think about this. F of x gives the miles that can be driven in x hours. So that's so I'm going to kind of relabel it. I'll check that later. Let's see. So we have this f of x gives the miles in x hours. So I'm just going to say the distance versus time, or miles per hour, right? Something like that. And then g of y, so a completely different function, gives the gallons of gas used in driving y miles. So the gallons based on a certain number of miles, right? Okay. And I'm putting miles as D here. Okay. Which of these expressions is meaningful? I think it's the second one. So g of f of x, ultimately that's going to give us what? The number of gallons based on hours driven, or hours given. Because f of x gives us the miles based on time, g of y gives us the gallons based on miles. So then g of f of x should give us the gallons based on time, right? So the number of gallons used in X amount of time driving, something like that, right? Gallons based on time. Let's see. Here it is. So the expression g of f of x, which is I think what we said, makes sense and will yield the number of gallons g used while driving a certain number of miles in x hours, right? Yeah, I think we're okay. Okay. So using this table, evaluate f of g of 3 and g of f of 3. Okay. So for the first one, we have f of g of 3. So let's look at the g of 3 first. So when x is 3, what's our g? So when x is 3, g is 2. So then now we use that as an input for f. So when x is 2, f is 8. So f of g of 3 should be 8. Let me see if I can do that one more time, right? Here we're going to just start with g of 3. All right, so when x is 3, our corresponding g is 2. Now we use that as input into f. So when x is 2, then f of 2 is going to be 8. So that first answer is going to be 8. So f of g of 3, our claim is that equals 8. Okay. So then now let's consider g of f of 3. First I'm going to find f of 3. All right. So when x is 3, f is 3. So f of 3 is 3. And then we use 3 as an input into g. So then next we're going to find g of 3. So when x is 3, g is 2. Okay. So we're saying that g of f of 3 equals 2. Okay. So even though both of these were evaluated when x was 3, the first one we had f of g of 3, we got 8. The second one we got g of f of 3, and we got 2. All right, so it's not commutative. Composition of function is not commutative. Okay, you see the 8 and the 2 there. Okay, let's keep going. Okay, I'm just going to kind of work this. So using figure 1, evaluate f of g of 1. Okay, so first we start with the inside function. When x is 1, we want to find the corresponding g. Okay, so when x is 1, it looks like g is 3. Okay, so then we take when x is 3 and evaluate it for f. So when x is 3, looks like f is 6. So then our claim is that f of g of 1 is 6. Okay, and that's correct. So figure 3 shows how we can mark the graphs. Oh, this is part of an analysis. That's fine. And that's, you kind of saw me do that where I was drawing the dashed lines. I was doing essentially this. Okay. Given this f and h, evaluate f of h of 1. Okay. So first let's find h of 1. So if we're going to evaluate h of 1, that's going to be 3 times 1 plus 2, which is 5. Then we want to take that and use that as input into f. So now we want to find f of 5. That's going to be 5 squared minus 5, which is 20. So sorry, guys. Yeah, it just hit me like, I don't know. I think we got 20. Yeah, that looks good. But we're moving pretty. We're making pretty good time. Not that I'm in a rush or anything. I'm just noticing. The domain of a composite function. So whenever I'm trying to find the domain of a composite function, there's a three-pronged step that I do. Right. So like if we have f of g of x, to find the domain, first I find the domain of the inside function, then I find the domain of the simplified function, and then I take the intersection of those two results. Okay, so let's see that in action. I feel like that'll be better. So here we're asked to find the domain of f of g of x. And I know if you listen to this, watching this video, I know I got you yawning. It's contagious. Oh man. Okay. Let's try to, I want to just like power through this and get it over with. Let me see. Okay, so the domain. So again, to find the domain of a composite function, again, there's a 3-step process. Let me see. So for the domain of f composed G, first we find the domain of the inside function. Okay. Second, we find the domain of the simplified function. And then third, we take their intersection. Okay. And I think I kind of want to shrink that down a little bit. Just a little bit. Shrink it down to make it feasible. I'm just, man, I already be kind of loopy. And then I get sleepy. You can like multiply that times KOKN 3 or something. I don't know. Anyway. Okay. The domain of the inside function. So if we have f composed G, our inside function is g of x, right? So if we're looking at this guy here, it's a rational function because we have a variable in our denominator. In general, the domain of a rational function is going to be all reals except any x that makes the denominator 0. Okay. So if we set the denominator to 0 and solve, we get what? X is 2 over 3, 2/3. So when x is 2/3, that makes the denominator 0. So we have to throw out 2/3. Okay. So the domain, for the first part, the domain of the inside function, we said everything except 2/3. So we said x is not equal to 2/3. Okay. Next, we'd like to find the domain of the simplified function. Domain of the simplified function. So what we're going to do there, we're going to go ahead and evaluate f of g of x. So our f of x is this. G of x is 3x minus 2 under 4. Okay. So one technique to simplify this is called a complex fraction, because whenever we have a fraction within another fraction, that's the definition of what we mean by a complex fraction. So in order to clear out some of these fractions, we can multiply by 1 in a certain form. I'm going to multiply by 1 in the form of the LCD over the LCD. There's only like the one denominator, the 3x minus 2. So I'm going to multiply by 1 in the form of 3x minus 2 on top and bottom. All right. Okay, let's see what happens if we do this. Now on bottom, it looks like this guy is going to cancel. It looks like we're going to have 4 minus 3x plus 2. And on top, it looks like we're going to have, I don't know, I'm running out of space, 15x minus 10. I'll keep working over here. So on bottom, we have 6 minus 3x. And on top, 15x minus 10. We could factor out a negative 3. No, that doesn't cancel anything. We could factor out 5. If we factor out a 5, that'll be 3x minus 2. Okay. So now, we're going to take this as our simplified function. So then the domain of this guy is going to be the same thing, all reals except any x that makes the denominator 0. If we set the denominator to 0 and solve, x equals 2, right? If we let x be 2, it creates a 0 in the denominator, so we have to throw it out. So if we're going to throw out x equals to 2, okay? So we found the domain of the inside function. We found the domain of the simplified function. Now the final step is we take their intersection. Okay, so we want to say x not equal to 2/3 intersection x not equal to 2. Okay. I really want some more space. Give me a moment. What slide is this? 22. Let's copy. Sorry, guys. Yeah, I don't know. I tried to do it when I had energy, and it's just not working. Okay. Right here. I want to paste. Okay. So we want to take the intersection of x not equal to 2/3 and x not equal to 2. Okay. So we said x is not equal to 2/3 intersection x not equal to 2. So then basically what we want to do is capture all numbers on the real line except 2/3 and except 2. Okay. So say this is my 2/3 here. Say this is 2 here. We want to capture everything except 2/3 and 2. So we want all the numbers to the left of this guy. We want all numbers in between. We want all the numbers to the right. And we use parentheses in both directions to show that we get really, really close to 2 and 2/3, but we don't actually reach those. All right, so once we have this image, then we transfer it to interval notation. So the far left is going to be negative infinity up to what? 2/3 union. Wait a minute. Yeah, I think we're okay. And we want all the numbers between 2/3 and 2. And then union, all the numbers to the right of 2. Infinity always gets a parentheses in this context. Because we don't want to include 2/3 and 2, they all get parentheses. Okay. All right, so that's the 3-step process I like to use to find the domain of a composite function. Okay, let's keep going. Let me see. So we're saying that it's basically everything except 2/3 and 2, and that's the same thing that they got. Everything except 2/3 or 2. Okay, sorry. We're almost there. Well, we're almost halfway. Find the domain of this where f is given and g is given. Okay, so for the domain of a composite, first we find the domain of the inside function. I'm going to abbreviate this. So the domain of the inside function. That's going to be the domain of g. So in this case, we have a square root function. So in general, we cannot take the square root or the even root of a negative number. So that radicand, that 3 minus x, has to be greater than or equal to 0. Okay, so in this context, the domain of the inside function, this 3 minus x has to be greater than or equal to 0. Okay. So then if we solve the inequality, 3 is greater than or equal to x. If we graph this, so say here's our number 3. If the alligator is eating a bigger thing, then the 3 is bigger than our numbers. So that means our numbers go off to the left of 3. Since we can be equal to 3, we're going to use a square bracket or a closed circle. So then, and now from here, we can write it in interval notation. Oh, wait a minute. Let me, before I do this, I'm kind of jumping the gun a little bit. Okay, so that's the domain of the inside function. Let's find the domain of the simplified function. Okay. Simplified, right? So I'll work here, I guess. So then f of g of x, this means f of the second function inside the first. Okay. So our g of x is the square root of 3 minus x. Okay, so what we're going to do is write f of x like normal, but replace each x with the green thing. Okay, so we got this x plus 2 inside the radical, but again, we're replacing the x with the green thing. 3 minus x, okay. So again, the inside part, the radicand, this square root of 3 minus x plus 2 has to be greater than or equal to 0. I think that domain, let me see. If we subtract 2, we're not going to have a square root equal to a negative number. So it seems like the only restriction is still that square root of 3 minus x, right? Or that 3 minus x, like what we had before. Because the square root, let me think about it. If I subtract and I square, oh, wait a minute, we might be okay. If I subtract 2, square both sides, so now we have what? 3 minus x is greater than or equal to 4. Let's see if that works. I think that's okay. 3 minus x is greater than or equal to 4. I don't know what I'm writing. Let me back up. Right here. Okay, that's better. So add and subtract. X is less than negative 1. Okay. So the first one we got x is less than 3. The second one we got x is less than negative 1. All right. I guess I'll color code these. So this one I'll do in blue. I'll do this one in orange. Okay. So then if we look at the number line with both of these guys, for the first one, x is less than 3, so we got 3 and negative 1. So here's our 3 here. Here's our negative 1 here. So the blue was talking about all the numbers left of 3, including the endpoint. The orange is talking about everything to the left of negative 1, including negative 1. So what points do they have in common from negative 1 onto the left? So then that domain is going to be negative infinity up to negative 1. Okay, sorry. Ooh. Okay. So now say we get a solution like this and we want to test if it works, right? So, you know, what we could do is choose a few points and check them to make sure that they make the original true. And then you can test points that should make it false, right? For instance, if we let x be -2, it should make the original true. Okay. So like when x is -2 right here. So double negative becomes positive. Square root of a positive is positive. So we get a positive result. Versus if we let x be 0, it should not work. So when x is 0, the square root of 3, we're going to leave it as a square root of 3. What do we do wrong? I feel like we're missing something. It may have been that squared set, but we might not be able to do that. Yeah, something's off. And part of it is because I'm sleepy. Like it's just harder. I usually like to do this when I first wake up, but I don't know. I've been short on time. What do they have in common? Everything left of -1. Let me see. Add and subtract. -1 is bigger than x. Add. 3 is bigger than x. Okay, I'm not seeing what I'm doing wrong. Let me see here. Because we can't take the square root of negatives. We got that. Yeah, negative infinity to -3. Let me see. I think it's the second one over here that we're messing up. That has to be greater than or equal to 0. If we subtract. Oh, okay. I found it. Yeah, I'm brain fog because I'm sleepy, right? I found it. So right here, when we subtracted the 2, and I'll do my markups in purple, or let's do this for now. Right here, when we subtracted 2, we had square root of 3 minus x is bigger than a negative, right? Well, because square root, is non-negative, the square root is going to always be bigger than a negative. So that domain was actually all reals, right? So I think when I squared it, I did make a mistake. So this one right here, this domain is going to be all reals. And we realized that something was wrong even before we checked the result because, when we tried our test point, the test point wasn't working, all right? 0 was actually making it true. So I was getting that second domain incorrect, right? The second domain is all reals. The first domain is x is less than or equal to -3. Sorry, less than or equal to 3. So this orange one really changes to the whole number line, right? It goes like this. Let me get rid of this too. I think this is wrong here. And let me change this color so you know this pertains to okay. Again, let me recap that. When we got to this line here, when we go to solve for the square root, we subtract 2 on both sides. We're going to have a square root is greater than a negative, right? Well, a square root is always, in this context, a square root is always going to be bigger than a negative. So then that domain is all reals. So then all reals intersection the blue. Well, what do they have in common? It's really just the blue. And that should be 3, negative infinity to 3. Okay. Yeah, I'm definitely gonna have to take I have one more section I'm trying to do, but I'm definitely gonna have to take a break after finish this one before I start the next one. Okay, so we kind of got to the bottom of that one. So write this function as the composition of two functions. Okay, so we kind of worked an example or two where given two functions and we were evaluating f or one function composed the other. So now what we want to do is start with the result and see, can we decompose it into two functions where we say one function inside the other function. Okay, so we're given that f of x equals the square root of 5 minus x squared, and we're asked to decompose it. I'm going to decompose it into two functions, g and h. Now the simple thing to me, I want to say g compose h. All right, when I do g compose h, I want my inside, the simple inside function to me looks like, let h of x be 5 minus x squared. Let g of x be the square root of x. So now when we do, well, we wouldn't do h of g, we would really do g of h of x to maintain, to put it in the proper order. Okay. So I got these two results for my other two functions. Okay. Yeah. So let h of x be 5 minus x squared. Let g of x be the square root of x. So then that way, when we do g of h of x, we get our original. No, that's not it. Let me back up. Right here. Over here. Where are my slides? Oh, did I just, is this the one where I had a whole bunch of extra? Oh, that may be it, actually. Oh, yeah, I think I did. Let me make sure. 3.4. This one. Composition of functions. I know one of these is right. View. Single page. Let's just go like this. I think this is the same thing going on. I just want to check a copy of the one that's correct to make sure that we got everything. I know I have one here. Done. Okay, 3.4. No, I think this is the same thing. I guess that's it. Okay, we're gonna let that be it. I hope it's it. Hang on, I'm going to keep you guys for just a moment because I don't want to walk away from my recording. Even though I could edit it, I just don't want to have to do all that. I'm gonna look at one more thing to make sure. I could have sworn I'd saved that update though. Okay. So let me check. Give me just a moment to check my other source just to make sure. Oh no! I really am sleepy. I think that is it though. Let me just check. Give me just a moment. Let me see. If I go here to PowerPoint, this is 3.4. Yeah. And I guess I just forgot to export the updated thing. Let me see. Yeah, I think that's correct because this one stops at 28. Yeah, that's right. Okay. So, yeah, sorry about that little confusion. Sorry for also yawning so much. I don't know. I can't get around it. So I'm going to stop this because we did get to the end of this section, take a nap, and then once I'm up, I'll go ahead and try to do the final recording for this week. All right, so with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.